Alright guys, we're going to look at number 4 as our sample problem for gas law stoichiometry. This is a pretty complicated equation to balance, so I'm going to just write the balance equation, or I'm going to put in the coefficients because balancing is not the problem here. We want to make sure you understand the stoichiometry. Alright, so we have our balanced chemical equation, and what we're going to do is we are going to start. So we're looking at excess HCl dripped onto 15 grams of potassium permanganate. What volume of CO2 will be produced? Alright, so our starting point that we're given is 15 grams of KMnO4. So we're starting at mass A. And the question is, what volume of chlorine will be produced? Okay, so we need to go from mass A to volume B. If we look at our mole map, mass A goes to mole A goes to mole B is going to go to volume B. So our starting point is 15.0 grams of KMnO4. Alright, and we're going to convert that to moles. So we have 1 mole of KMnO4. And our grams of KMnO4, alright, we're going to fill in. Alright, you're going to calculate the molar mass. Then from here, I'm going to go from mole A to mole B. And mole B, I'm going to use my balanced chemical equation. So I have moles of KMnO4 on the bottom. And based on the balanced chemical equation, that's 2. I have 2 moles of Cl2 up top. This is going to give me moles of Cl2. Alright, I'm then going to use the answer here, this moles of Cl2, in my equation PV equals nRT. Alright, this is the equation which is going to bring us from moles B to volume B. Now, in order to fill in this equation and solve for V, alright, because that's what the question's asking, I have to put in the pressure that is given to me. And the pressure is already in atmospheres, so I don't have to worry about converting atmospheres. So 0.959 times V equals N, and N is what we solved for here. So I'm going to call this N. R is a constant, and T is 15 degrees Celsius. However, I have to add to that 15 degrees Celsius 273 degrees, and that's going to give me 288 Kelvin. So I'm going to put 288 Kelvin in. Alright, I'm then going to solve for V. Alright, remember, you're solving for what N is. You're going to plug N into the equation here, and then you're going to give me an answer for V on Monday. Alright, that's your example for gas law stoichiometry. Alright, this is what you need to be able to do. Now, one of the other problems that we have to deal with is Dalton's Law of partial pressure. This is a law that's dealing with gases, and we're not dealing with Mr. Dalton, the English teacher. We're dealing with John Dalton. And the best example of Dalton's Law is dealing with the atmosphere or the air around us. The pressure of the air around us is a combination of the volume of that air made up by all of the gases in the air. So the main 2 gases are nitrogen and oxygen in the atmosphere. 79.11 kilopascals is the pressure of nitrogen. 21.22 kilopascals is the pressure of oxygen. Alright, we have a combination of a few of the other smaller gases. Alright, but the total pressure is 101.3 kilopascals. This is sea level pressure. Well, in order to get the total pressure, we're going to add the pressures of each of the individual parts. Now, Dalton's Law is going to be used in the lab or in questions where we collect a gas over water. So if we were to collect the gas over water, all right, we'd have a beaker. In that beaker, we'd have water. Inside that beaker, we'd have some type of collection vessel. That has a rubber stopper in it, or some type of stopper. All right, this collection vessel would have markings on it, looking at its volume. We'd be having outside this some type of reaction going, and this reaction produces a gas. Now that gas that's produced from the reaction is going to move through this tubing and fill this collecting tube with, this collecting tube has water, and it's going to push that water down, and we're going to be able to figure out how much gas we have. So in this collecting tube there is water, all right, as well, and that water gets pushed down and comes out this tube, all right, and what we do is we collect gas above and we can measure that gas. When we do this, the gas is going to exert some amount of pressure downward, all right, and that pressure is going to equal a certain value. However, because we're collecting this gas over water, the water exerts a pressure as well. All right, because the water, depending upon temperature, always forms some vapor. So if we look at this problem, all right, we want to look at a sample of oxygen collected over water at 25 degrees Celsius and 760 torr. What is the pressure of the dry gas? All right, so we have pressure of the dry gas. All right, here we have our total pressure, okay, and that total pressure is going to equal the total pressure of the dry gas plus the pressure of the water. So if our pressure total is 760 torr, the pressure of the dry gas is what we're trying to determine. The pressure of water is a constant which is always going to be given to us. All we're going to do is subtract 23.8 on each side. And this is going to give us the pressure of the dry gas. So 760 minus 23.8, and that's going to come out to 735.2 torr. Now, we can then use this dry gas to determine the same pressure, or to look at volumes under different conditions. All right? But this is how Dalton's law applies to pressure of a dry gas that is collected over water. All right? So those are your notes. Enjoy your Easter weekend. I'll see you in class on Monday.